Hello, students. Today we will discuss the second and third mode of transfer of heat, that is conduction, convection, and radiation. We already discussed about the conduction. Now we will discuss about the convection and radiation. Before starting convection and radiation, let us recapitulate the conduction. When we heat a metal strip at one end, the heat travels from one end to another end. As we heat the metal, the particle vibrates. This vibration makes the adjacent particle to vibrate, and so on. So the vibration are passed along the metals, and so it transfers the heat. And we call this as conduction. Now, the metal are different. The outer electrons of the metal atom drift and free to move when we provide the heat. If we provide heat to the metal, the free electrons of the metal get kinetic energy from the thermal energy, and because of that, the electron free to move here and there, and with taking the kinetic energy, and they transfer the heat from one portion to another. The C of electron are gaining kinetic energy and transfer it through the metal. Whereas in case of insulator, such as wood and plastic, do not have the C of electron, which is why they do not conduct heat as well as the metals. Now we have an example. We have two rods. One is made of metal and other is wood insulator. The metal conducts the heat away from hands, and wood does not conduct the heat from our hand as the metals. So wood feel warmer, whereas the metal we feel con- the colder one. Now, second mode of transfer we have to introduce today, that is convection. What happened to the particle in a liquid or a gas when we heat it? Look here, the particles are closer when they are cold. And when we heat it up, the particle spread out and becomes less denser. In second figure, they are far away from each other. So they becomes less denser. This affects fluid movement. The particle goes away from each other and fluid will get a movement. Now, when the cooler particle we think they are more dense and fluid sink through the warmer, less dense fluid. So cooler goes toward the warmer side. In effect, warmer liquid of gases, as gas are also the fluids, they are also move from one point to another. So they are less dense, so they rise up. Hence, we may say the cooler liquid and gases sink, whereas the warmer liquid and gases rise up. Now, here we have another example, that is the water movement. Here, the water is heated by the burner. What happened? The hot water molecules rises as they become less dense. That's why they moves up. Whereas the cooler water sink down because the molecules are more denser. This produces the convection current. The flow of fluid because of convection is called convection current. The another case of convection is, why is the windy at the seaside? Because there is a lot of temperature difference between warm land and the colder sea. When land becomes warm, the gases start to rise. The air above rises. And when they approach to the certain height, they become colder and denser, and they again come down to the sea. So they will make a convection current near the sea. That's why there is a windy at sea's height. Another example, we use a freezer compartment and put in a fridge. The freezer compartment is put on the top of the freezer because cool air sink. The cool air sink, it is sink downward and cool the food stuffs near them. They cooled the food stuffs near them. And as the cooler one come down, the coldness will be reduced because the air get some heat from the food stuff. So the warmer air will rise up. The air is taken, the cool air is taken some heat through the food stuff and they will go up. And this process will continue and produce the convection current. Now, what happened here? Here we have an ultimate source of energy, that is sun. And we are getting energy, the heat from sun. As there is no material between sun and earth, so the heat cannot be transferred through the conduction or by the convection. Hence, we will say there should be a third mode of transfer of heat, that is called radiation. Now, what is radiation? It is the method of transfer of heat from one place to another in form of electromagnetic radiation without necessity of medium. and without affecting the intervening medium. So the electromagnetic waves which are coming from sun to the earth, they need not any medium because they are able to transfer through the vacuum. And even if there is any medium between them, the medium will not affected by them. The radiation is emitted by an object on account of its temperature, and its major component is infrared radiation. Example, the heat from sun comes to us through radiation. On standing near fire, we feel hot, or heat comes to us through radiation. Now here is sun, and the radiation is coming from the sun, and a person is laying. The area of the person is A, and the heat radiation is coming, making some angle, that is theta. If the area of the person is A, then the area perpendicular to the radiation will be A cos theta. This A cos theta part is also responsible for the season. As we know, the axis of Earth is tilted by 23.5 degrees through the equator. So the angle is theta. The area affected by them is A cos theta. Because of this leaning of axis, there is a seasonal change. Here we consider the light rays are coming from sun in the month of June. They are mostly falling on northern hemisphere. They are mostly falling on northern hemisphere because the angle is 23 with the axis of rotation. Hence, the northern hemisphere will get a summer season. Because theta is 0 here, if theta is 0, the cos theta will be maximum. So the heat radiation will fall maximum on this part of the earth. Whereas theta increases by 50 degree across the southern region, hemisphere. So A cos theta will be very smaller than A. That's why there will be a winter season. And at pole, what will happen? The theta becomes 90 degree. So radiation will not present there. So it will be extremely cold. Now, basic characteristics of thermal radiation are the radiation is fastest mode of heat transfer. It is fastest mode of heat transfer. The energy is transferred along a straight line with the speed of light. That is 3 into 10 to the power 8 meter per second. The second is they require no medium for their propagation. They can propagate through vacuum too. They do not heat the intervening medium through which they pass. It means the medium is not affected by the radiation. They obey inverse square law. As the intensity varies, inversely as the distance increases with its square. They can be reflected and refracted just like as the other part of the light. So they will follow the law of radiation, reflection, and refraction as well. Like light radiation, these radiation also exhibit the phenomena of interference, diffraction, and polarization. So these are the basic characteristic of thermal radiation. Now let us consider some question to us. The first one is the radiation travel in straight line. The statement is correct, so it is true. The second question is radiation can travel through a vacuum. The answer is correct, so the statement is true. This radiation require particles to travel? No, the radiation does not require any particles. So the statement is false. And the last one is radiation travel at the speed of light? Yes, every radiation travel with the speed of light. So the statement is true. Now the use of thermal radiation is in thermography. The detailed measurement of the radiation from the body. Here we measure the radiation of body and it is used for medical purposes and it is called medical imaging. The warmer area of the body may be sign of the tumor or infection and the cooler area of the skin may be sign of poor circulation. Now we will discuss some terms related to the radiation. The first is the reflectance, second is absorptance, third is transmittance, and the radiation depend on the nature of the surface of body. Wavelength of incident radiation. Now let us consider here about the reflectance, absorptance, and transmittance of the body. If we have any object and the radiation is falling on them, if the radiation is represented by Q and the object is receiving the radiation, some part is reflected, some part of them is absorbed, and some part of the reflection will be transmitted. And this depends on the nature of the surface of the body. Then the heat which is coming in form of radiation is Q, and it is now divided into three parts: R plus A plus T. If we divide this one by Q, then it is Q by Q is equal to R by Q, plus, 2 q, 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 A by Q plus T by Q. The ratio of reflectance to the total amount of heat radiation coming is called reflectance, and it is represented by R. The amount of absorbed heat to the total amount of heat radiation is called absorptance, and it is represented by small a. And the energy which is transmitted to other side of the object to the whole amount of energy which is coming in form of radiation, the ratio is called transmittance, and it is represented by T. These are depend on the surface of the body and wavelength on incident on them. Now, if we consider we have a body which is not transmitting, only the radiation which is coming on them is giving reflection and the absorption. Then at this condition, the transmittance T will be equal to 0 because nothing is transmitting. So from the equation R plus A plus T is equal to A, 1, we will get R plus A is equal to 1. Now if any body object is neither reflecting nor transmitting, it is absorbing all the amount of heat coming from radiation, then we say R is equal to 0, that is reflectance is 0, the transmittance is 0. From the equation R plus A plus T, that is the sum of reflectance, absorptance, and transmittance, it is equal to 1. So what we will get here, we will get A is equal to 1. Now let us consider about the black body radiation. When thermal radiation incident on the body, they are partially reflected, partially absorbed, and partially transmitted. As we discuss here, Q was the thermal energy, R is the amount of thermal radiation reflected from the body, and A is the amount of thermal radiation absorbed by the body in same time. T is the amount of thermal radiation transmitted by the body in same time. So we already discussed Q is equal to R plus A plus T. That is thermal radiation energy plus absorption radiation energy plus transmitted thermal energy will be equal to the total radiation which is coming on the object. And we again recapitulate. Small r is equal to capital R by Q. That is called reflectance. It is the ratio of thermal radiation reflected by the object in the given time of the total amount of thermal radiation incident on the body in that time. And second one is the absorptance of the body. It is defined as the ratio of the amount of thermal radiation absorbed by the body in a given time to the total amount of thermal radiation incident on the body in same time. And the last one is the transmittance, and it is represented by small t. It is the ratio of the amount of thermal radiation transmitted by the body in a given time to the total amount of thermal radiation on the body in the same time. So we get R plus A plus T is equal to 1. A perfectly black body, as I discussed earlier, when there is no absorptance the radiation will be reflected and transmitted. And if the object having no reflectance and transmittance, it means the total amount of heat is absorbed by the body. It means the reflectance will be zero, the transmittance will be zero, there will be only absorptance as R plus A plus 1, T is equal to 1, then 0 plus A plus 0 is equal to 1 in this case when all the heat thermal energy which is coming in form of radiation is absorbed by the body. So A is equal to 1. In this condition, the radiation of every wavelength, all the wavelength which is coming in form of radiation incidenting on the object is absorbed. Then we say that object is perfectly black body or perfect absorber of radiation. Since a perfectly black body neither reflect nor transmit any radiation, so absorptance is unit. At normal temperature, it must be appear black because whatever the wavelength which is coming on the black body, whatever the wavelength or whatever the frequency of radiation, whichever is coming, all are absorbed by the black body. All are absorbed by the black body. So, if a person looking this body, if a person is looking this body, there is will be no reflectance. So the person will look this body as a perfectly black body. It will appear black because nothing radiation is coming to the person or to the eye of the person. If a perfectly black body is heated, now just is opposite here. Now if we take this perfectly black body, if it is heated, then it will emit all possible wavelength. It will emit all possible wavelength. It means the range of the wavelength will be 0 to infinite. The perfectly black body will radiate all possible wavelength. This is very important term. The black body absorb all the wavelength, and if black body heated, then it will radiate all the wavelength. The range start from 0 to infinite. That's why we say the black body radiation is full radiation because if it is heated, it gives all the wavelength, or it is also called temperature radiation. Now we will discuss about fairy black body. As nothing is there which is a perfectly black body, but there is an arrangement. This arrangement is called fairy black body. In this fairy black body, it consists of a hollow double-walled metallic sphere. Here are hollow double-walled metallic sphere and with a very narrow opening. The opening is very narrow. It is represented by N here. with a conical projection in front of this hole, that is narrow opening, there is a projection which is in conical shape, which stop direct reflection incident on them. If there is any direct radiation on them, this will reflect it inside this cavity by this conical shaped projection. From inside, the sphere is coated with black color. In practice, it is the lamp black. This lamp black coating absorbs nearly 97% of the radiation. When radiation falls from this hole, then the 97% will be absorbed by the black coating of lamp black, and 3% will be reflected. 97 will be absorbed, only 3% will be reflected. And after this one, again it is 97% absorbed, and a very, very few amount of the radiation will be reflected. But this reflection will engage inside the cavity. So the cavity, that is fairy black body, absorb all the radiation. So that's why it is called a perfect black body. Now, if this fairy black body heated, if this fairy black body heated, it will radiate all the wavelength through this narrow hole. Thus, the opening of the body, this fairy black body, is called black body radiator. Now we define some terms. The first one is the monochromatic emittance, or the spectral emissive power of the body. It means the black body is now heated. For a particular temperature, the amount of radiant energy emitted per unit surface area of the body per unit time within unit wavelength, that is near the wavelength lambda. The unit wavelength is lambda plus half and lambda minus half. So it is represented by E lambda. It means the perfectly black body is emitting some wavelength, and the emissive power is corresponding to this wavelength at a particular temperature, is defined as the amount of energy radiant per unit surface area. The area is taken as per unit surface area. Per unit time, that is in 1 second. And the wavelength limitation is lambda half and lambda minus half. This is called monochromatic emittance. But the emission is not only of a particular wavelength. For a black body, there are all possible wavelengths for radiation. So emissive power of the body at a certain temperature is defined as total thermal energy, total thermal energy emitted per unit area per unit time for all possible wavelength. So what we will do, we will integrate the monochromatic emission with respect to the wavelength, as spectral emissive power for a particular wavelength is E lambda, and for all the radiation we will integrate it with respect to wavelength from 0 to infinite, and this is called emittance, that is E. And the unit of emittance is watt per meter square or joule per second per meter square. Next point is monochromatic absorptance, because black body may also absorb the radiation. So spectral absorptivity of the body, represented by A lambda, is called monochromatic absorptance. For a particular wavelength, for a particular temperature, the amount of energy absorbed per unit area, per unit time, and the wavelength ranges again lambda half to lambda minus half. The unit will be again same as joule per second per meter square or watt per meter square. Now here is the Kirchhoff's law. The ratio of emissive power, that is emissivity, to the absorptive power for a corresponding particular wavelength at a particular temperature is constant. So E lambda, that for a particular wavelength, this is the emissive power or emittance divided by the absorptance for that wavelength is always constant. This law is called Kirchhoff's law of radiation, and this is represented by capital E lambda. The capital E lambda is called emissive power. The capital E lambda is called emissive power for a perfectly black body for a particular wavelength at a particular temperature. So E lambda by A lambda is constant, hence E lambda is equal to constant into A lambda, or E lambda is proportional to A lambda. The statement of Kirchhoff's law now state the good emitter are good absorber, because E lambda is proportional to A lambda. So good emitter are good absorber. Similarly, in vice versa, the A lambda will be proportional to E lambda. And for perfectly black body, the emissive power will be 100%, that is 1. At that condition, E lambda will be equal to A lambda. This is known as Kirchhoff's law. Now here we have two experiments. The first one is the emission experiment. Here we have four containers, one made of shiny metal, the other cylinder made of dull metal, then dull black, then shiny black. We fill warm water inside them of same temperature at same time. Then you have to find out which container will be warmest after 10 minutes. Think about Kirchhoff's law of radiation. The shiny metal container would be warmest because it has good reflectance and the water is inside this metal container. The water molecules which are having heat will give radiation to the wall of the container, and it is a very good reflector as it is shiny metal. So the radiation will come again inside the container. In next radiation they fall on other side of this cylinder, then it will again reflect. So the radiation is captured inside the container. So the radiation will remain inside the shiny metal container. Hence, there is a very small amount of loss of heat. That's why the shiny metal container will be warmest after 10 minutes. Whereas the dull black, we may say they are good absorber. So they are also good emitter. The dull black container would be coldest because it is best at emitting heat radiation. As dull black are good absorber, that's why they are good emitter. Just opposite to them, we take the absorption experiment. Now all the four containers having water inside them are now heated by the burner in same time and with same amount of temperature. All of them are heated. Which container will have warmest water after 10 minutes? The dull black container would have warmest water because it is good absorber of heat as well as it is good emitter of heat. And the shiny metal would be coolest because it is poorest at absorbing heat. So the heat will be reflected back from the shiny metal. That's why it will remain coolest. So dull black will remain warmest after 10 minutes. That's all today. Thanks for watching.